Okay, welcome to class 11. Today we're going to look at some conversions here. Let's go ahead and just dig into the material and get to that in a second. All right, first thing, an NFA, to review, an NFA, which is what we talked about last time, was just like a DFA defined by this quintuple. And that quintuple, if you remember, works exactly like a DFA except for one change. And that one change is in the transition function, delta here. And so the only difference is that we not just have Q cross alphabet, but Q cross alphabet union lambda. So that allows us to have lambda transitions, or parts of the transition function that can change state on lambda. And the other part that maps to a set of possible states it could transition to, not to a single state. So in other words, the main differences are lambda is allowed to cause a transition. And the second thing is the transitions, when they happen, can go to more than one place given some symbol or lambda. And one final thing is the transition function doesn't have to be a total function. Okay, so NFAs are like DFAs, but allow lambda transitions, change state for no reason, not obligated to, but could if it wanted to. And the other thing was having multiple transitions leaving a state with the same symbol. And that's what kind of this change in the transition function caused to happen. And that makes the NFAs non-deterministic because they can decide or choose whether to use the lambda or not use the lambda. Or they could decide, given a symbol that has multiple edges leaving a state going other places, it could decide which one it wants to take. So given an A, I could do this, or I might do this. So we're kind of giving it that choice of what it wants to do with it. And here was our example. It's not a DFA because we have lambda transitions. It's not a DFA because it's not a total function. Like there's nothing leaving Q2 that says A, nothing leaving Q4 that says B, nothing leaving Q1 that says B, nothing leaving Q3 that says A, nothing leaving Q0 that says A, and then we have these lambda transitions. So you'll note that that's definitely not a DFA. Now, the one thing about NFAs is, so now into new material. So we reviewed that quickly. Let's look at a couple new things here. So we asserted that NFAs, even though they kind of have this non-determinism and have this free will, if we want to call it that, this ability to decide what to do, that does not make them any more capable than regular expressions or DFAs. You would think that it would. You'd think giving them this non-determinism would somehow give them a power to decide things, which would give them more abilities than a DFA or regular expression would have. But they're not. They're not any more capable. And today we're going to confirm that. We're going to prove that by doing conversions from one of the three to the others of the three. All right. So when it comes down to it, regular expressions, DFAs, and NFAs can only define languages that are in the family of regular languages. And that means that if there's a representation for one, then there's a representation for another. So in other words, if I have a regular expression, it defines a language. I could also make a DFA that defines that language. I could make an NFA that defines that language. So they're all really the same set, the same family of languages, regular languages. Now, so we've seen these three ways of defining languages: regular expressions, DFAs, and NFAs, and all work differently. They have different sets of rules. They kind of function differently. These second two are machines that also act as acceptors. The first one, regular expressions, is kind of more like an algebraic expression form of representing languages. And the question was, is any one method more powerful than the others, and is any one method less powerful than the others? And we're going to look more closely at that, and as we're going to find out, the answer is no. None of them is more powerful. Not one of them is more powerful than the other two, and not one of them is less powerful than the other two. Okay. So back to those questions. Is any method more powerful than the others? Is any method less powerful than the others? And the answer is, it turns out they're equally capable, which means that for any regular expression, we can make an NFA that defines the same language. For any NFA, we can make a DFA that defines the same language. For any DFA, we could write a regular expression that defines the same language. So they're all equally capable. And that family that they define, again, regular languages. Now, there are languages that are not regular languages, which means that if I have a non-regular language, I could never make an NFA, I could never make a DFA, I could never make a regular expression for those. So if it is a regular language, I can make all three, and if it's not a regular language, I could not make one of them. They're all equally capable and equally incapable. Okay, so to illustrate that kind of equivalence, we're going to look at a way to convert from a regular expression to an NFA. And if I can do that, that means that every regular expression has a corresponding NFA. So let's start by reviewing the rules for making regular expressions. And if you remember back to when we talked about regular expressions, there were two classes, the primitives and the composites, which use operators of some sort. So let's look at the regular expressions here. So regular expressions, they're the primitives. Lambda defines the language just consisting of the empty string of lambda. Empty set defines the empty language. A defines a language just consisting of the letter A, if A is in the alphabet. And then we have the composites, the union operator, the concatenation operator, the star closure or clean closure, and the positive closure. And then in parentheses, a regular expression, which doesn't change it. It just is used, parentheses don't change the language. It's just used for grouping. Okay, so let's start looking at how we would convert each one of those. So the idea behind this conversion to an NFA is if we could make an NFA to account for each one of these conditions or possible types of expressions, meaning a lambda, what does an NFA for that look like? What does an NFA for empty set look like? What does an empty set for just a symbol from the alphabet look like? And then if we could make it an NFA for each of these, what does it mean when we have some language union with another? What does that NFA look like? And if we could define a NFA that describes each of these possible conditions, then we could take any regular expression, we'd have a rule for converting it, we just substitute that NFA type for whatever came from this. All right, so let's start off with the primitives. So the primitive regular expressions, you'll note that lambda, empty set, and just a symbol from the alphabet. So let's create an NFA for each of those. So the first one there, lambda. Well, here's an NFA that would represent just the language lambda. We have a start state or a state, and on lambda it transitions to another state, and that other state is final. So that means when I get lambda, I slide across, and I've accepted that. What about the empty set? Well, that should not ever accept anything. So here we have a final state, there we have a start state, and there's no way to get to there. So we could never get get out of this Q0 to get over to Q1. So it's disconnected. There's no way to accept anything. No strings would be accepted by this. And the last one with an A is going to look familiar. It looks just like the top one with the lambda, but a single A gets us from start to final. And I suppose each of these should be labeled with a little start arrow to show it's where it starts, but just kind of implicitly Q0 in this case is representing the start. All right, so that's the primitives. We've covered all those. Going back for a second. Oops, there's the primitives. We've got all three of those. There they are. And now let's move on to the composites. So the union operator, we have some language R, regular expression R, union with some regular expression S. And for each of these, R and S, there exists some NFA for it that has its own start state and its own final state. So what we're doing here is we're going to tie the machine for R together with the machine for S, and the way we make it a union is we basically give it two possible paths to get to this final. So we connect from our new start state into the start state of each of those two machines, and then we connect from their final state or states into a new final state F, and we connect those on lambda. So notice now, what are the ways I can get from Q0 to F? Well, I could go through the machine for R and then go to F, or I could go through the machine for S and go to F. So that's kind of, we've been reading this regular expression as or, R or S. So how do I get from start to finish? I have to go through R, or I have to go through S. And whatever these look like could be other machines that get created in this kind of constructive way like that. Now let's move on and look at the one for concatenation. That looks like this. Here's the machine for R. We pipe that or connect that to the machine for S, make a new start state, make a new final state, connect all of that together with lambdas. So how do I get from Q0 to F? Well, first I have to go through R, and then after that, I have to go through S. And so here is R followed by S, or the concatenation of RS. And there's a machine that we can make for that. And notice that these are kind of dotted lines around here, indicating that this would just be another NFA that was plugged in that was constructed from the either other primitives or other composite things. Now, the star closure, what's that look like? Well, star closure, remember, was 0 or more occurrences of whatever R is in this case. So here's the machine for R. How do I get 0 or more? Well, I make a new start state and a new final state, and I make a lambda that bypasses it. That's the 0 part of R. So 0 times through R, I just skip it. Or one time I could go straight through here, through R. Or if once I've gotten 0 or I've gone through, if I want to have another R, now I have a lambda going from the final back to the beginning that lets me get more. So notice I could get 0 of these, or 1, or go through and get 1 and then slide back through the lambda and get another one, and slide back and get another one. So I can have 0 or more by spinning through from F back to start, or Q0, as many times as we want. Now, what's the positive closure? Well, positive closure is 1 or more, so that's going to look just like the star machine, but it doesn't have the lambda going from the start to the final. So here's 1, and then it can jump back and get more. And then finally, R in parentheses, what's that look like? That's just R. So we don't really need to do anything with that. Parentheses don't change the language. They're just used for grouping. But in this case, I just went ahead for symmetry and added the Q0 and the F as the final state. So we slide through the lambda, we do everything that R would have done, and we slide through to F, and we have the same thing as lambda. R lambda is the same as just R, and so that's what this is defining. And that is all 5 of the composites. So now we have all of the primitives, we have all of the composites, and now we can do any regular expression we can make an NFA from. Let's look at an example. So in our example, we have A followed by A or B star. So let's start out with the stuff in parentheses, since that's what would happen first here. So A or B. So remember what A would look like. It's just a state sliding through to another state on A, and B is the same thing, state sliding through to another state on B. So let's look at that first. So step 1, A union B, or A or B. Well, there's what that looks like. There's A, there's B. Remember, we had those dotted lines. We can make a new start state, a new final state. I don't have this labeled final right now because we're not at the end of the whole process. But notice that how do I get from here to here? And notice I've left off the labels on these. So just imagine this is Q0, this is F, or our final state. So here's, how do I get there? Well, either A or B. There's 2 paths. It's one or the other. Now let's do step 2. Step 2 is now applying the star closure to that whole thing. So we're going to take this whole machine and put it inside of that pattern we saw to make it a star, which means make a new final state, make a new start state, connect those in on lambda, and then make it bypass it on lambda, make it go back to the beginning on lambda. So now how do I get from here to here? Well, I could skip it, or I could go A and back, or B and back, and I can get as many A's and B's as I want there. So now the next step from that is the concatenation, which is concatenating A on the front of this whole thing. If you remember how we did that, the pattern for that was here's A, here's the thing that we just created. So to concatenate them, we create a new start, create a new final, connect those on lambda, connect this on lambda, and now we go through A first. So this is going to be A followed by A or B star, and now we have an and now we're done. We have an NFA that is complete. Now, moving on, converting another kind of conversion. Converting a DFA to an NFA. And this one is actually really easy because it's already done. So DFAs are just a restricted form of an NFA that doesn't allow lambdas and doesn't allow multiply defined edges and is a total function. But notice that still falls into the category. We've just taken some certain aspects away from an NFA, but it's still an NFA. So DFAs are already NFAs. So note that all DFAs are NFAs, not all NFAs are DFAs. So a DFA is a restricted form or subset of, if we make the transition function with more restrictions, with no lambdas and no multiply defined edges, then we have a DFA. Okay, converting an NFA to a DFA. Now, not all NFAs are DFAs, but can we convert one to make it the same? And the answer to that is yes, they're all the same, but we're going to look at an algorithmic way to do that. Before we do that, let's remember what the language defined by an NFA is. A language defined by an NFA, the language of that machine M, is all strings that are in our alphabet or over our alphabet, such that if we start at the start state and consume that string and do the extended transition function, that meaning consume symbols, we're going to end up with some state that is a final state. So another way to think about that, all strings over our alphabet where there's some way to get to a final state. All right, so let's look at the algorithm for doing this conversion. Okay, now I just listed it all out here, but let me go through it anyway. So the idea is we compute the extended transition function starting with the start state on lambda. And that's going to basically tell us what are all the places I can start. What are all the states I could possibly be in when I start? And then we're going to label, we're going to create a vertex in our DFA graph that we're creating. We're going to make a circle, make a vertex, and we're going to label it with the set that this produced. Because remember, the extended transition function of an NFA produces a set. So we're labeling the vertex that we created, that initial vertex, we're labeling it with the set that comes out of this function. And then after we've done that, then we're going to repeat the following until there are no edges missing from our DFA graph, or G sub D. So first we pick a vertex that has a missing edge, meaning that we found a circle in our graph where there's a symbol from our alphabet that does not have an edge leaving that node on the graph, that vertex on the graph. So we choose a vertex with a missing edge from our alphabet, and then we compute using that symbol that was missing from the set of states that are in that vertex. In other words, I'm going to say, what are all the places I can get to from using this symbol from all of the states that are in my vertex that I'm looking at? And that's going to create a new set of states. So the result of that, if it's an existing vertex, we just add an edge, draw an arrow from that state to the one that it transitioned to. Otherwise, we add a new vertex that's labeled with what this could have gone to, and then we add an edge to that and label it with that symbol. And then we repeat that until every circle, every node in our graph has an edge for every symbol of our alphabet in it. And at that point, we now have a total function. And after that, we just see we have to figure out which ones are final states and which ones aren't. So step 4 here, any state, any vertex whose label contains a final state, that should be a capital F there. Here, let me fix that while I'm looking at it. So any state that has in its label of its graph, in its set, a final state, not all of them have to be final, just one, then I make that a double circle in my graph, or a final vertex. And then I just relabel them all from the sets that they had and give them a numeric ordering 0 through n. And now I have a DFA. Now this will make a little more sense when we look at an example. All right, so here's an example. And in this example, notice we have the two states, Q0 and Q1. Well, first off, I don't see any lambdas. So is this already a DFA? And the answer is no, because notice from Q0 I have an A leaving. And notice from Q0 I have an A staying there. So I have two divergent edges here on A, where it has free will. When I give it an A, does it stay in Q0 or does it decide to go to Q1? It's up to it. So that makes it not a DFA. There's one other thing that makes it not a DFA. And maybe you'll notice that. It's not a total function. We don't have an A leaving Q1, and we don't have a B leaving Q1. So we don't have anything. This is not a DFA for a couple reasons. multiply defined edges leaving a state, and also edges missing from some states, not a total function. All right, let's look at our conversion and use our algorithm. All right, so step one, we start with our start state, which is Q0, compute the extended transition function of that on lambda. And notice that means when I start, where can I go on nothing? And right now, there's no lambda transitions leaving this. So the only place I can go when I start is just Q0. But it's a set that comes out of this extended transition function. So we're getting the set containing just Q0. And we add that initial vertex. There's a circle. It's an initial one. It's got the little arrow coming into it. It's Q, labeled Q, the set as the set Q0. Now, step two, we say for any edge that's missing, well, Q0 does not have an A and it does not have a B, so let's start with A. So we say from the set Q0 on an A, where can I get? So looking at our NFA again up here, Q0 on an A can go back to 0, or on an A it could go to 1. So I could be in 0 or 1. So that's the set 0 and 1 is the output of this. And then I don't have a vertex labeled 0 and 1, so I make one, and I connect from 0 where I was on A through to 1. All right, so next step. Next step is compute the extended transition function on Q0 and B, because I don't have a B accounted for leaving this yet. There's a missing edge, so let's add the one for B. So we look up here on Q0, the set Q0 on a B, where can I go? Only back to Q0. So this loops back, Q0 loops back to Q0. Now I look at this graph and say, do I have missing edges? Well, yeah, well, Q0 is fine. I have an A leaving it. I have a B leaving it. But Q0, Q1, I don't have anything leaving it at all. So I need to do A and B for that one. So moving on to the next page, let's compute from Q0, Q1 on A. So here's the NFA up here. And you can't really see that right now. I'm going to take my picture off just temporarily here so you can see that. So you'll notice here's the NFA. So on 0 and 1 on an A, what are all the places I can get to? So on 0, I can get to 0. On 0, I can get to 1. On 1, I don't go anywhere, so it's still 0, 1. So because that's still 0, 1, we add an edge, leaving 0, 1, going to 0, 1. And there it is looping back to itself. So you'll notice from 0, 1 back to itself on A, and you can see that right here, from 0, 1 to 0, 1 on an A. Step 5, we have a missing edge. We don't have anything for B leaving 0, 1. So from 0, 1 on a B, what are all the places I can go? So we look at our NFA up here. So on a B, I can only go back to Q0, so Q0 stays where it is. So Q0, Q1 on a B goes to Q0. So 0, 1 on a B goes to Q0. And now we look at that and say, do we have any missing edges? And I don't, because this first state, Q0, has an A and a B leaving. 0, 1 has both an A and a B leaving. So we're done with step 5. So step 6 is there are no edges left to be added, no symbols left to be added. So we mark the final state. Any of these that contain a final state, there's only one final state, was Q1. So if any of these contain Q1, it becomes a double circle, and there it is there. And then the last step here is to relabel them. And now I've just labeled what was this first one Q0, and the second one I labeled Q1. And now you'll notice that we have a DFA. So here's what the NFA looked like, and here's what the DFA looked like that came out of it. And just to kind of idiot check ourselves, is this a total function? Yes. And let's try a few. So A should definitely accept. Does A accept here? Yes. What about AB? AB does not accept. AB does not accept. But you'll notice that what's cool about this technique is this will work on any NFA, and it'll pop out a DFA. This is called the subset construction method or theorem for converting NFAs to DFAs, but we're creating kind of these, you can see why that's called that. We're creating these like subsets of where it could go, and then constructing this DFA as we go along. Now, there's one other technique I want to show you quickly that will make this easier, because looking at these graphs can get confusing. This was a really simple example, but looking at the graphs and trying to figure it out can be like you maybe would miss an edge, or you'd have something where you start drawing it and then you work yourself into a corner where you can't get out. You have edges crossing other edges and make a big mess. Well, there's an easier way to do that, and that's called this table-based conversion method, or the table-based subset construction method. And this method is useful because it will track those states and which edges are missing in that table without ever drawing a picture. We can do it all in the table. So let's look at that previous example, and we'll look at how that works with the table-based method. All right, so here we go. So to start out, we still compute the extended transition function on lambda. In our case, we said that was just Q0. So that's where our table starts. And then what we do is we list the state, which would be essentially our labels for our vertices. And then across the top, we're also listing each of the symbols of the alphabet. In our case, we only have an A and a B, so we just put A and B in the table. Now the next step we do is we say, okay, if I have an empty slot in the table, I need to figure out what it is. So I say Q0. If I'm in Q0 and I get an A, what do I do? So Q0 on an A, well, notice I could stay in Q0. Or on an A, I could also go to Q1. So this has to now be 0, 1. So let's add that to our table. So boom, it gets added, 0, 1 gets added, and now we have that entry in the table. Now, Q0 on a B. So Q0 on a B stays in Q0, so we put the set Q0 there. So that gets added. Now what I do once I'm done with that is I look at the things that I added, and any of them that have not already been listed in our table, I add them. So that one we just did on B, we don't need to add that because that already exists right there. But this 0 and 1, that does not exist in our state column over here, so we need to move that down. So we move that down. So this didn't exist, so we moved it down to there. And now 0 and 1 is in our table, and it has some spots that we haven't filled in yet. So 0, 1 on an A. So 0, 1 on an A, what do I do? Well, 0, 1 on an A can go to 0, can go to 1, that's it. So we add the 0, 1 set in there. Now we have an empty spot for B. Well, 0, 1 on a B can only go back to 0. So we add that, and now that we're at the end of the table, we look back at it and say, well, 0, 1 I already have, 0 I already have, so I'm done with the table now. So the next step for this is to relabel them. So when I do this, I usually like to create another new column off to the left here. That's the relabel, and I just number those 0, 1, 2, 3, 4, however many there are. And then I also identify which ones are final states. So in this case, I put 0 there, I put 1 there, and then 1 because it has Q1 in there from the NFA was a final. We make it a final state. And when I actually draw these out rather than writing final, I usually put a circle around the ones, or a double circle around the ones over here. So we relabel and identify the final states, and then we draw it out using all these things substituted for this. So anywhere I saw 0, 1, it becomes a 1. Anywhere I see a 0, it becomes set 0, it becomes a 0. And so we wind up with that same picture we had earlier. And notice how much easier that is to keep track of what's going on, because we just work our way through the table, building it until no new states get created. And then we have a DFA. And you'll notice that you might say, well, what if this keeps going on forever? What if it just keeps making states and states and states and states? And the answer to that is it really cannot do that. And the reason it cannot do that is, well, there's a couple reasons for that. But the main reason is, if you think about the set of possible states that could get created from, or subsets of states that you could have, that has to have a limit. And the limit of that is the power set of the number of states. And since it's NFA has a finite number of states, the power set is going to have a finite number. So we are bounded by the size of the number of possible states in our DFA being the power set of the states in the NFA. This one came out to be smaller than that, but there might be some that are bigger, but they have to be finite. The process will not go on forever. Eventually we'll end up with a table that's all filled in, that has all of these transitions, edges labeled. The states will eventually stop creating new ones, and then we have a DFA. This will work every time. Now, we've proven we can go from a regular expression to an NFA. We've proven we can go from an NFA to a DFA. But we really need to close the loop on this and say, what about a DFA back to a regular expression, or an NFA to a regular expression? And we're going to save that for next time. But one thing I do want to do here is try another example on paper before we're done for the night, just to show you this. So let me go and switch the, here, I'll turn me back on. And I'm going to turn the, no, that's not what I want. Switch to that. All right, let me line this up. All right, so now we're on the document camera. Let me just do a quick example here of this. And we're going to use the table-based method because I think that's easier to follow. All right, so let's do this. Let's say, here's the NFA. NFA, let me make sure you can see that. It's a little blurry. There we go. So my NFA that I'm creating is going to look like this. Let's do, here's my start state. I'll call that Q0. And let me identify that as a start state with my little lightning bolt arrow. And let's have that feeding back to itself on a 0. And then let's say on a 1, let's go to another state here. And here I'm out of frame, so let me move this over. I don't know if it matters. All right, so let's label this Q1. And let's also make it another 1. Goes down to Q2. And let's on this, label this as 0. And I'm using 0s and 1s instead of A's and B's here. Let's go to a final state. Let's make that Q3. And let's make down here a 1 and have that go to Q4. And I apologize for that camera losing focus whenever my hand goes in and out. I think it's trying to find my hand and focus on that, or the top of the pen maybe. All right, so here's our NFA. So we want to convert that to a DFA. So let's go ahead and make the table for that. So the table for that is going to have, first off, what is our starting state? Well, what's the extended transition function on lambda? What are all the places I can get to on lambda? In this case, nowhere. I don't have any lambda. So it's just going to be, so let's make our table. So state, and then 0 and 1. That's supposed to be a 0. Looks bad. Here, let me just draw this like that. All right, so there's my table. The start state is Q0, the set containing just Q0. Okay, now we are ready to start actually filling in the table. So Q0 on a 0. What are all the places I can get to on a 0 from here? So on a 0, I can only get back to Q0. So here, Q0. What are all the places I can get to on a 1? Well, 1 and 2. I can go to there, or I can go to there. 1 and 2. So here I'm going to put Q1, Q2. And now we look at the line. Did we have any that we just added that we already don't have a state? Well, yeah, 1 and 2 we didn't have. So Q1, Q2. And now Q1, Q2. So Q1, Q2 here. We're looking at both of those. On a 0, where can I go? Well, Q3. Q3. Q1, Q2. On a 1, where can I go? Q4. Now, do we have any that already don't exist on our table? Yeah, Q3 and Q4. So Q3, we're going to have to add that one. Q4, we're going to have to add that. All right, so now we're down the next line. Q3 on a 0, where can I go? Nowhere. Now, that we need to label. That's the empty set. Q3 on a 1, where can I go? Also nowhere. Empty set. Now, empty set doesn't exist in our table, so we're going to add it. And now we go down to Q4. Q4 on a 1 or a 0, nowhere. Q4 on a 1, no edges leaving that, so nowhere. And then empty set, we're not in any of these, so we can never go anywhere on empty set, empty set, empty set, empty set. So there's what our table looks like. Now we're going to Let's go ahead and redraw that DFA. And I'm going to draw it first without relabeling it. So this is going to look like this. So we're going to start in Q0. And actually, let me make that the set Q0. And then on a 0, it stays there. On a 1, it goes to 1, 2, Q1, Q2. And then Q1, or I need to label that 1. And then Q1, Q2 on a 0 goes to 3. And on a 1 goes to 4. These are sets. And then Q3 on a 0 goes to empty set. So let's draw that. That's on a 0. On a 1, it also goes to empty set. Q4 on a 0 goes to empty set. On a 1 goes to empty set. And then finally here, we have empty set going back to itself. On a 0, we have it going back to itself on a 1. And I apologize for using a red pen. I should probably use a black one. It's a little bit hard to see. Now, I now have all of these edges labeled in that thing. I just need to identify which ones are final states. Well, anything with a 3 or a 4 in it. So this has a 3 in it, so that's going to become final. This has a 4 in it, that's going to become final. And now let's redraw. And relabel these. So this I'm just going to call Q0 now, rather than the set. So that has a 0. This one I'm just going to call Q1 now. It's going to go up here on a 0 to a final state, which I'm going to call Q2. And then here's another final state down here, which I'm going to call Q3. Or actually, this needs to be a 0 up here. This needs to be a 1 down here. And now over here, we have Q4, which is not a final state. And that's going to go down there on a 1. It's also going to go down there on a 0. This is going to go up there on a 0. Also going to go up there on a 1. And then this is going to stay here on a 1 and stay there on a 0. And now we have a DFA. And I cut that off a little bit. Let me move that up so you can see it. So now we have a DFA. Notice every vertex has all symbols from the alphabet. That's 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. It's a total function. No multiply defined edges ever leaving anything. And this is guaranteed to define the same language as that we have up there. And all right, so there's an example. Let's do one more example here. So just if you're looking at this, this was example 1, page 1. Let's look at one more. And I was hoping I had a different pen other than red, but I don't seem to, so I apologize again. All right, so this is example 2. I'll put a 2 up here. Make sure you can still see what I'm writing. Okay, so this one I'm going to start out like this. I'm going to start out, so this is the NFA. Q0. And let me make this one loop back on a 1. Let me make it also loop back on a 0. And now let's put Q1 and Q2. And let's make this go to there on lambda. Let's make that go there on lambda. And now over here, let's take a 0. Make this one final. Make that Q3. Let's put that as 1. Make this Q4. And make this one final. All right, so there's my NFA. Let's make the table. All right, so the table, we have state, we have 0, we have 1. All right, so where do I start? So extended transition function from 0 on lambda. What are all the places I can get to on lambda? Well, I could get to 1, I could get to 2, but I could also stay in 0 because lambda, remember, they're not obliged. In other words, if I'm in 0 and I have no input, what are all the places I can get to? I could be there, or I could have slid through to 1, or I could have slid through to 2. So the start state on this one is going to be Q0, Q1, Q2. That's my start state. Now on 0, 1, 2, on a 0, what are all the places I can get to? Well, I could have stayed here and then slid through to 1, 2, so 0, 1, 2, but I could also go to 3, so 0, 1, 2, 3. So this one's going to be the set Q0, Q1, Q2, Q3. And I apologize that that's hard to see. That's 0, 1, 2, 3. Now on a 1, what are all the places I can get to? Well, here I am in 0, 1, 2. What are all the places I can get to from there? Well, on a 1, 0, 1, 2, or 4. So this is going to be Q0, Q1, Q2, Q4. I tried to write a little bigger there. So now I don't have either of these states in my state list, so I need 0, 1, 2, 3. So Q0, Q1, Q2, Q3. I didn't have that one, and I also don't have Q0, Q1, Q2, Q4. So I've added 2 new states. All right, so let's look at those. From 0, 1, 2, 4, or let's 0, 1, 2, 3. From 0, 1, 2, 3, so all of these up here, what are all of the places that I can get to from these ones on a 0? Well, 0, 1, 2, 3. So that one stays there. So Q0, Q1, Q2, Q3. What about 0, 1, 2, 3 on a 1? 0, 1, 2, 3 on a 1? Well, 0, 1, 2, 4. Q0, Q1, Q2, Q4. Now, 0, 1, 2, 4 on a 0. 0, 1, 2, 4 on a 0 is going to go 0, 1, 2, 3. Q0, Q1, Q2, Q3. And then on a 1, we're going to go to Q0, Q1, Q2, Q4. And now we don't have any new ones that got created here that weren't already in the table. So we just need to identify which ones are final states, any of them that contain a 3 or a 4. So this is going to be final. That's going to be final. Let's draw the DFA version of this now. So here's my start state, which was 0, 1, 2. And in this case, I'm going to go ahead and do the relabel of these. So this is going to be the new Q0. So new. Can you see that? Yeah. Q0, Q1, and Q2. Those are my new labels. This one's going to be final. That one's going to be final. So I'm just going to go and label these. So here's Q0, the new one. And then we're going to have a Q1, which is going to be final. And we're going to have a Q2, which is final. Now, Q0 was this one. On a 0, it goes to 0, 1, 2, 3, which is now 1. So on a 0, that's going to go up there. On a 1, Q0 is going to go down here. So that takes care of that one. And now Q1 on a 0 is going to go or stay there. So on a 0, we're going to go there. On a 1, it's going to go down here. And then 2 on a 0 is going to go back to Q1. And on a 1, it's going to stay there. And at that point, we've accounted for all the edges. If we count the edges, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. we have our three states. And now this becomes our DFA. And notice that's a total function. And this is going to be guaranteed to represent the same regular language that does. Okay, so I'm going to draw one of these for you to think about and ponder. And I'm not going to solve it right now. And here, I'm going to do this one with a different. Let me do. Let's see if this is easy to read. This is 3. Yeah, that looks better. Okay, so this one, I'm going to draw the NFA, and I'm going to leave it for you to ponder. All right, so let's say here's Q0. That's my start state. I'm going to use A's and B's instead of zeros and ones. There's an A. There's an A. Q1. I'm just making this one up as I go. And I'm also going to put a lambda down here. Lambda down to Q2. I'm going to make Q2 final. And I'm going to make this on an A go down there. I'm going to make this also go down there on a B. And then I'm going to put an A up here to Q3. And I'm going to put a B down here to Q4. And then I'm going to connect this back to there on lambda. Okay, so there's my NFA. And what I want you to ponder is, what does the DFA look like for that? And make sure you can read all that. That's an A. And notice it's clearly not a DFA right now. We have multiply defined edges leaving in different places. There's an A leaving here or staying there, another one going over there. There's an A here going up there, one going down there. This is not a total function because that doesn't have an A leaving it. There's a lambda transition back to Q1 where this thing goes in the circle. So what does the DFA look like for that one? And I'll leave that for you to kind of ponder for next class. Let me go and switch back to the presentation for a second. So we did a few more examples, and that's all I'm going to cover today. You might want to be ready for a quiz and an assignment. The next assignment, you're going to do some of these conversions from regular expression to NFA and from NFA to DFA. And eventually we're going to add one additional thing, and that's DFAs back to regular expressions, but we're going to do that next class. So that's it for today. Everybody stay safe, and I'll see you soon. Look for the assignment. Be ready for a quiz. Good night.